So it's my pleasure to welcome Dr. Daniela Korčáková. And I'm sorry, Daniela, we haven't had a chance to practice, so I hope that was okay for the pronunciation. Dr. Korčáková is currently Associate Professor at the Astronomical Institute of Charles University in Prague. Daniela did her training at Masaryk University in Brno before then taking on a position at the Astronomical Institute of the Czech Academy of Sciences with a year program at Tübingen University, and finally joined the Charles University some time ago. And today, Daniela will be regaling us about FS CMa stars. So, Daniela, without further ado, I'll leave it to you.
Okay, thank you very much. Is it okay? Can you see slides, hear me, everything?
Yes, all good.
Super, super. Hello, and thank you very much for the possibility to show you our work. I'm going to talk about FS Canis Majoris stars. These stars are totally overlooked, which is very, very pity, as we will see. FS Canis Majoris stars are stars showing the B-Brachydie phenomenon. So they have forbidden emission lines and strong infrared excess. These spectral features point to very extended circumstellar region. Forbidden emission lines and infrared excess have stars of different types and in different evolutionary stages. Henny Lammers, with his colleagues, they found B-Brachydie stars among Herbig AEB stars, supergiant, compact planetary nebulae, and symbiotic stars. But they were not able to classify about half of stars known in that time. Partially it was because of bad data, but it was also because some stars didn't fit to any of these groups, and several of them maybe even in more of these groups. Later, Anatoly Minoschnichenko recognized that these unclassified stars have similar properties, and he started to call them FS Canis Majoris stars. So please keep in mind during my talk that FS Canis Majoris stars are something like a garbage of B-Brachydie stars. So in the list of FS Canis Majoris stars, there are some young planetary nebulae, some symbiotics, also some Herbig AEB stars, interactive binaries, and as we will see, also post-mergers. FS Canis Majoris stars have strong infrared excess. This is due to the presence of warm dust, and some of them have a sign also of cold dust. To find dust properties is really something very tricky. But nevertheless, Gauba with his colleague, they were able to find the composition of the dusty grains in MWC 939. And they found that there are two dusty rings. The inner one is composed from graphite grains, while the outer one from silicates. The dusty region is very clumpy, and sometimes also huge clouds are created. And these clouds may cover the star. And this was really observed, for example, in FS Canis Majoris itself. FS Canis Majoris stars are typical by the presence of forbidden lines. We always detect forbidden lines of neutral oxygen, usually also forbidden lines of singly ionized sulfur and nitrogen. If we detect lines of sulfur and nitrogen, so we may use nebular diagnostic. Forbidden lines are very narrow and symmetric, and sometimes they are double peaked. FS Canis Majoris stars have a very strong Balmer emission. For example, H alpha may be 100 times more intensive than continuum. As higher member of the Balmer series, as the line is weaker and narrower. But this is nothing special. It's just the radiative transfer effect in every emission line star. But what is very specific is a pretty large number of Balmer lines, and this gives the limit to the density and also turbulent velocity. Depending on the angle of view, we may observe a very strong absorption of iron group elements in UV. This is called iron curtain. The absorption may be so strong that UV flux may be reduced about an order of magnitude, which is possible to see in this picture. The upper spectrum is a spectrum of classical B star OMI Andromeda, and down is a spectrum of HD 50138. Of course, spectra are recalculated to the same distance. We also detect material ejecta and inflow. This is visible very well as discrete components of resonance lines. They are usually blue-shifted, but sometimes also red-shifted. The material inflow and ejecta reveals also themselves as P Cygni profiles or inverse P Cygni profiles in absorption lines of helium and metal lines. The lines are very variable and on many timescales. Absorption lines show night-to-night changes. Emission lines vary on scales of weeks, months, and years, but everything together. And forbidden emission lines are more stable. They show changes on scales of months and years. The even more complicated is photometry, because now the dust enters the game. And usually is observed something like multiperiodicity. And also observation shows that period changes must be taken into account into the analysis. I think the best example is photometry of MWC 342, because it was systematically followed for a few seasons. And always there was detected a short period from 14 to 16 days, and also the longer one from 40 to 120 days. The longer one sometimes disappeared. But the data were sufficiently good, so this shouldn't be just error of analysis. So it seems that such behavior is typical for FS Canis Major stars. Recently, we found very strong magnetic field in IRAS 17449 plus 2320. The magnetic field modulus is around 6 kilograms, so it's on the order of the strongest magnetic AP stars. And it's really a magnetic field because we measured doublets, triplets, and also quadruplets, and all these lines gave the same value of magnetic field modulus. Moreover, the value of magnetic field modulus change with the rotation period, as we will see later. If we put together all the pieces that gives us the observation, we may draw this picture. There is a magnetic B star. It's a slow rotator. It's probably also pulsator, and the interference of pulsation modes may play there a role. Sometimes we observe material ejecta. It's detected very well as a discrete component of absorption of resonance lines. The star is surrounded by a gaseous disk, but this disk is far from to be homogeneous. There are some rotating arms, spots, expanding layers, and also we detect expanding layers that decelerate. And time to time, some material fall back onto the star. Depending on the angle of view, we see iron curtain. This gaseous region is really in strong non-LTE conditions. The multiple scattering plays there an important role. Especially important is the coincidence of wavelengths of resonance lines, because such the way the spectral lines of different elements are coupled. So also there's variability. But luckily, FS Canis Major stars are rather cold B-type stars. So the radiative pressure doesn't play such an important role. Behind this gaseous disk, there is dusty ring. Sometimes there are two of them. If there are two, so they have different composition. The inner one is from graphite grains, while the outer one from silicates. And the dusty region is really clumpy. Sometimes huge clouds are created and they may cover the star. So all these things together creates a really huge mess in observed properties. So there is no wonder that the nature and evolution status of FS Canis Major star remain a mystery for a long time. There are several attempts to explain these stars. The first, what came into the mind, were Herbig A-B stars. It was natural because spectra of FS Canis Major stars are almost identical with the spectra of Herbig A-B stars. But FS Canis Major stars are located far from the star-forming regions, so they cannot be young. The spectra are also very similar to post-AGB stars. And indeed, in the list of post-AGB stars, there is several FS Canis Major stars, but they have slightly different properties. So it's not explanation for all of them. What about this would be just an extreme case of classical BE stars. The name is almost the same, but that's it. Classical BE stars don't have forbidden emission lines, and also they don't have dust, and if so, only a little bit and with different properties. But classical BE stars are fast rotators, while FS Canis Major stars are slow rotators. Currently, the widely accepted scenario is current binarity. It's the simplest explanation of a huge amount of gas and dust. Especially dust is very problematic. And indeed, there are several binaries among FS Canis Major stars. But the clear evidence of the secondary is only about 1/3 of these stars. The problem is circumstellar matter. Because thanks to it, the observations as well as analysis may be misinterpreted. And the clear evidence of this, and in about 70% of FS Canis Major stars, every sign of the binarity may be explained by something else, something easy and also very reasonable. And this percentage of binarity is the same as in main sequence stars, because FS Canis Major stars are rather cold B-type stars. The problems cause also literature. Instead of helping us, it does the opposite. There is really total mess. For example, if in the original paper with observation, if there is written something like, we find a slight signs of binarity, the following paper in the interaction, one can read they found that it's binary. And few years after that, in the interaction they appeared, they proved that it's binary. And this is general behavior. One must really follow every original paper with observations or analysis. I'm not very convinced that every FS Canis-Major star is a binary. We published the first long-term observations of FS Canis-Major stars. And we always found variations of equivalent with radial velocities, intensities, V over R changes. And sometimes it really seems like a regular periodicity. But when we add there more data, it was clear that this is not a regular periodicity. We also model bisector variability, and we were not able to fit the data with binary model. From principle, it was not possible. But I'm sorry, I'm not going to discuss all the arguments in favor and against binarity. It would require at least 1 hour. And instead, I would like to focus on our new results that point to another nature of FS Canis-Major stars. There is a scenario that explains all the observed properties, and this offers merger. Of course, this is not scenario for every FS Canis-Major star, but as we will see, there may be several post-mergers. The merger naturally explains a huge amount of circumstellar matter, because the matter is ejected before the merger through the Lagrangian point L2 during the merger and also after the merger. After the merger, the star rotates very rapidly with critical rotation, and the decretion disk may be created similar like in BE stars. And also some FS Canis-Major stars are hot enough to create a wind from the inner parts of the disk. The merger scenario may be the explanation for some FS Canis-Major stars first indicate the observations of De La Fuente, because he found 2 FS Canis-Major stars in the central parts of 2 clusters. There is something wrong with binary hypothesis through interferometry. Because Kluska, with his colleagues, they were not able to explain VLTI observations of HD 50138 by the binary model. Only one would work was the disk with a spot. But the strongest argument for the merger is that FS Canis-Major stars are slow rotators. It maybe seems strange because when 2 stars merge, so they rotate very quickly, they are really rotated by critical rotation. But during the merger, thanks to the mixing, the strong magnetic field is created. And as stronger the field is, as faster the star slows down. Another support for a merger scenario is observation of lithium resonance lines. If this would be just ordinary binary, so detection of lithium lines would be a clear evidence of secondary. But there is circumstellar dust around FS Canis stars, and the line may be formed during the disk. Moreover, it may be something similar like in Arabic AE stars, because in some Arabic AE stars also lithium resonance lines are detected, and polarimetry show that this cannot be from the secondary. Some FS Canis Major stars have very strong lithium lines, and this indicate that they may have overabundance of lithium. And lithium overabundance found Kaminsky in about half of red novae, so nova-like events thanks to the merger. The question, of course, is if it's even possible, because when one has two ordinary stars, so the probability that these stars will merge is essentially zero. But stars are formed from molecular clouds, and for some time they remain in a cluster, and cluster dynamics may play an important role. So therefore, we started with N-bunny simulations, and we found that about 1.7% of stars are involved in mergers, and that about 50% of mergers are B-type stars. So it really does make sense to search for mergers in FS Canis Major stars. Once we found that it's reasonable, so we started with 2.5 dimensional magneto-hydrodynamic simulations. And up to now, these simulations explained all observed phenomena. So geometrically, take disk inhomogeneities, expanding and decelerating layers, material infall and ejecta, wind from the disk, matter in the corona, and also hot corona. Another support gives HR diagram, because FS Canis Major stars are located around the terminal H main sequence. So let's compare it with simulations. The best simulations of merger evolution has Schneider. He calculated this evolution for 2 O stars, but it doesn't matter. Still, we can see a lot. This evolutionary track is plotted by different colors, and colors indicate the rotation velocity. The scale of the rotation velocity is on the right of the picture. And as we can see, the star rotates rapidly after creation. But in only about 1,000 years, it slows down. And it's exactly in the region where there is a terminal H main sequence. So it may correspond to observed place of FS Canis Major stars. From this simulated HR diagram, we can see also another region. So from before the star reach the main sequence, so it's overluminosed. And when we would like to find the mass of the star with just standard evolution tracks, so we obtain a larger value of mass than it's in reality. So that means that the colder FS Canis-Major star may become magnetic AP stars when they enter the main sequence. Once the star enters the main sequence, it evolves as the ordinary star. It may be magnetic, may not, may have peculiar chemical composition, may not. Everything depends on the mixing during the merger process. So the best argument for the merger scenario would be to find at least one post-merger. And I think we found it. It's this star, IRAS 17449 plus 2320. It's the first magnetic P bracket E stars. So why I do think that this star is a post-merger? First, it has very strong magnetic field, and this field may be generated during the merger. It's also slow rotator, fitting the standard synthetic spectra. We found that the rotation velocity is about 9 km per second. But this value is overestimated because the standard technique interprets the Raman broadening as rotation 1. So in reality, the star must rotate slowly. This star has also a very large space velocity, especially toward the North Galactic Pole. It means that this escaped from the cluster. Why this is important? The binaries that were kicked from the cluster, so they have usually very large eccentricity and very short semi-major axis. And in this situation, the tidal forces circularize the orbit, and as a consequence of momentum conservation, the semi-major axis shrink. So the binary may, or of course, may not merge. This star has also UV excess. The magnetic field modulus is plotted here on the right picture. But as we can see, the error is pretty large. So therefore, Iris Bermejo-Lozano and Greg Wade, they started with the polarimetric measurements. And they didn't follow a line after the line. They combined information from all nice lines. Nice lines is, as usual, not weak, not overexposed, not blended. And the profile, intensity profile is plotted on the bottom picture is the lower one. Above is the Stokes V profile that describes the circular polarization. And integrating this Stokes V profile, one obtains longitudinal magnetic field strength. And Iris was able to plot a nice phase diagram with the period of about 36 days. And this period is rotation 1. Because the phase curve is nice sinusoid, so that means that the pole is a dominant geometry. From the picture, we can also see that there must be a significant angle between the rotational axis and magnetic axis. This is because there is a shift in y-axis. And also, we had observations for about 18 years, and such a beautiful phase curve means that the magnetic field as well as rotation speed are relatively stable during these 18 years. Currently, we are working not only on the determination of the magnetic field structure, but together with Colin Folstrom, we work on fitting of synthetic spectra. IRAS 17449+2320 is definitely not a textbook case. It's a little bit hotter than classical AP stars. So it's not possible to use magnetic null line, a list of magnetic null lines, because it was created for AP stars. And up to now, we were not able to find any useful null line for the analysis. Therefore, fitting of standard synthetic spectra gives large errors in effective temperatures, log G, chemical composition, and also V sinus I. Also, this simple parameter is problematic because standard spectra, standard fitting of spectra gives overestimated value of V sinus I because the Raman split is interpreted as rotational broadening. So therefore, we use Raman code. It was written by John Landstedt, Greg Wade, and now also by Colin Folstrom. And this code includes the solves the radiative transfer through atmosphere of magnetic stars. Because IRAS 17449+2320 is not so much contaminated by circumstellar matter, so we may determine the chemical composition with pretty high accuracy. So we can maybe find if it's a merger or not. We complementary to polarimetry and also spectroscopy, Ondřej Juhas started the analysis of test data. So now is the question if it's even possible to see these objects. And to answer this question, Nela Dvorakova, František Dimbír, and Pavel Koupa, they look at the dynamical evolution of 510 clusters. They use the distribution of mass of the clusters based on the observations of Milky Way. So they have two very massive clusters and 256 low mass clusters. And they found that about 1.7% of stars are involved in mergers. And this one is even underestimated because they included only binaries and not multiple systems. So let's have a look on the result. Pretty much mergers is all massive stars. But there is a peak, the second highest peak corresponds to A stars. So it's in agreement with observations because we have pretty much magnetic AP stars. But what's even more important of us is this tail of the distribution, because thanks to this, 50% of mergers are B-type stars. It's just a natural consequence of initial mass function, initial distribution of binary star parameters, and the fact that the range of masses of B-type stars is very high. Majority of mergers occur during the common envelope phase. It's about 67%. But the stars may merge also before on the main sequence. And among these stars, maybe stars that were kicked from the birth cluster, because such binaries have very large eccentricity, short semi-major axis. And in this situation, the tidal forces circulate the orbit, and as consequence of momentum conservation, the stars may or may not merge. To see if our calculations are real, we compared it with observations. As the best parameter, we choose W component of space velocity. Of course, we had to rescale the distributions because we have many more calculated mergers than observed mergers. We also must remove the region along the galactic equator because there is a huge extinction, so simply we don't see the stars. As we can see, it doesn't fit so well, but at least the main trend is similar. Once we had all the set of simulations, so we of course ask more questions. And one of these is how many mergers are in individual spectral types. To my knowledge, this question hasn't been answered before. So let's have a look what it is. The second column shows the percentage of stars of individual spectral types at the beginning of the simulations. The third column is a percentage of stars of the given spectral type that are involved in mergers. And the third column is a percentage of mergers of the given spectral time compared to all mergers. And the last column shows how many mergers we can find in individual spectral type. So for example, O stars, there is only a few O stars in the cluster. So that means that they will not enter so much into merger process. Sorry. And that also means that there will be not a large percentage of all mergers compared to every merger, because from 2 M stars, it's not possible to create O star. But there is the largest ratio of mergers among all type stars. And that it's in agreement with other simulations and also with observations. So once we found that it really does make sense to search for FS mergers in FS Canis-Major stars, so we started with 2.5 dimensional magneto-hydrodynamic simulations. Alicia and Rao, they used Pluto code with initial conditions based on the observations. So slowly rotating magnetic star, circumstellar disk, resistivity, and in some calculations also viscosity and density that was measured around FS Canis-Major stars. And they really found that the disk changed significantly. First, it's thicker. And okay. Also, this is very inhomogeneous. There are some gaps and also some matter concentrations. And these matter concentrations may move toward the star, but also out from the star. And this is called backflow. They also found that depending on the initial conditions, there are several regimes of matter accretion. It may be just ordinary as in non-magnetic stars, so through a stream in the equatorial plane. It may be also that the matter from the disk follows the magnetic field lines. This is called funnel effect. But in these stars, there is this certain range of conditions where the funnel effect is unstable. There is a really very weak flow in the equatorial plane, and for some time the funnel effect, so the stream along the magnetic field lines may reach the stellar surface, but for some time it may be trapped in the region between the disk and star. It's exactly plotted here. So and sometimes from this region, the matter can be ejected from the star. They also found that magnetic field lines are twisted very much, and that the twist is really very fast. And this configuration must be unstable. So it's reasonable to assume that there is a magnetic reconnection, and that the released energy may heat the corona. And indeed, in some, or actually only up to now, only 3 FS CMa stars, the Raman lines have been detected. The corona may be fitted either by the wind from the disk, as is plotted in this density picture. It may be also fitted by the jet from the inner part of the disk, and sometimes hot plasmoids, so this vortex on the picture is created. Their simulation also show a very important phenomena, and that's that the matter flow is not stationary. It's plotted in the on the left bottom picture. There is a radial velocity at 2 stellar radii, and as we can see, the matter accelerates or decelerates, and this is very important for the measurements of mass loss rate, because mass loss rate may be found only based on the comparison of observations and calculations. And up to now, there are only 3 calculations of mass loss rate in FS CMa stars. And all these cases assume beta velocity law or something similar. Important is that they assume a smooth law for the velocity, so that the matter expands freely toward the interstellar region. But if the matter is accumulated around the star, so this technique gives a highly overestimated value of mass loss rate. And indeed, we detected expanding and decelerating layers in MWC 342. Because some of Herbig A-B stars show very complicated structure of the magnetic field, so we also ask how the matter distribution will change when we will include quadrupole or octopole. And the result of the density is plotted on the left pictures. Upper panel shows dipole and bottom quadrupole. But much more interesting is a combination of dipole and quadrupole. It's on the right. In this simulation, the strength of dipole and quadrupole is the same. And yeah, I don't think if you, maybe you can, nice. You can see this. So here where ends the arrow. There is created a clamp, and this may be responsible for the observations of discrete absorption components of resonance lines. So as you can see, we spent a lot of time and effort studying these stars. So why we are doing this? The answer is in this picture with HR diagram. Because post-mergers are out of the thermal equilibrium, so they are overluminous before they enter the main sequence. So it may happen that the coldest FS Canis-Major stars are the progenitors of magnetic AP stars. FS Canis-Major stars may be also the explanation for strange magnetic, very young white dwarfs. This was discovered only 2 years ago. And these mergers may also contribute to the chemical evolution and dust production in the galaxy. Moreover, our simulations show that there are also merger events that happen out of the galaxy. So they may contribute to the enrichment of intergalactic medium. And because these objects are out of the thermal equilibrium, so we can test our star structure and evolution models. So now the question is, if every FS Canis-Major star is a post-merger? Definitely not. The group was defined based on infrared properties. So it's really not a sufficiently sharp criterion. In the list of FS Canis-Major stars, we can find some post-AGB stars, supergiants, B X-ray binaries, some young planetary nebula, and also symbiotics. But definitely, there are some hot candidates for post-mergers. For example, HD 50138, FS Canis-Major itself, and also maybe WC 342. But what about, there is something more. What about, we have just in front of our eyes the evolution sequence of mergers? Why? I don't think so. This star, MWC 349, is interacting binary. It's something like a small eta Carinae, where two winds collide. But here, it's maybe better to talk about wind-atmosphere interaction. And it's even better for the creation of the dust, because one of the important parameters for the growing of the dust is relative speed, and this is small in this case. So it's in a similar situation like in common envelope phase, and star may, of course, may not merge. So I hope I was able to show you that there is many interesting phenomena and processes in FS Canis-Major stars, and that they deserve our attention. And I also hope that we have enough time for questions. So please feel free to ask.
Yes, so let's thank Daniela for this very interesting talk. And yes, we'll open it up to questions. So you can either use the, oh, yes, Stan, go ahead.
Nadia, thanks so much for this interesting follow-up to the discussions we had in Kazakhstan. I'm learning more and more about this all the time. I have lots of questions about different things we can always follow up. Let's start with, for example, if there's the supposedly 50% of mergers are B stars, and we associate mergers with generating a magnetic field, but when we see magnetic field incidence around the O, B, and A stars, it's always about 8 to 10% independent as you go from stars that are maybe 50 solar masses down to stars that are only a couple of solar masses. And so I'm a little bit, I think the idea of trying to predict mergers from n-body simulations is a challenging thing to do. And but I guess what I'm trying to say is if we do associate magnetic fields with mergers, then something is giving us magnetic fields independent of the mass, because 8 to 10% is pretty much uniform throughout that. Could you comment a little bit about how the n-body simulations?
Yeah. I also first.
Yes,
Okay.
go ahead.
For a long time, I was really very skeptic with n-body simulations. But Frantadin Zbira, he shared with me the office. And so I found that nowadays it's something very different as a few years or decade before. That everything somehow describes the real observations. So, for example, initial mass function, initial distribution of the binary star parameters are compared with observation. Of course, not straightforward, because they must run simulations and after that compare it. And also the evolution of binaries are included there with caution, so that once the code detects that the binary is too close, so it started like a cycle in a large cycle and recalculates the evolution of the binary and guess if it merged or not. So that's something what we can I think now use very well. And to the second question of magnetic field in hot stars, I just started to learn things about magnetic fields, but as I understood from Schneider paper, it's not so simple because everything depends on the mixing. So also on the opacity, and I think we have only, or Schneider has only one very nice simulation of merger evolution. So we will see. I mean, it doesn't have to be exactly 50%, but I think that it's pretty reasonable to remember or to think about it, to take into account this, because when you look at the distribution, so that the distribution will have this shape is something reasonable. It's somehow smooth. If it will be sharper or wider, that's the question of another analysis and observations. But I don't think that it will change so much that there will be no merger among B-type stars.
Thank you.
Okay. Any other questions for Daniela?
I have one question, Alex. So
yeah, go ahead.
Daniela, you have said that you have pretty good data for the past 18 years for the system on the rotation and other things. So because this system has such a huge magnetic field, we should be able to measure the spin down rate over this 18 years. Is that something you actually have? I mean, your slide size is very stable, but perhaps you could actually measure more precisely the spin down rate from this 18 years of data. Is that something you have done, or is that a possibility?
I don't think that now we reach sufficiently high precision because the point which we have here, so it's everything what we have from polarimetry, and the magnetic field modulus is not sufficiently precise. That's the question of following observations. If we can we can find changes in rotation.
Okay, thank you. I have one more question if no one else has one. Yeah. Okay. So in the second to last slide, you were showing this Alicia's simulation, 2.5D MHD simulations of the system, and yeah, you have shown that infall material. I think maybe it was, I don't know, maybe the previous slide. So you showed those. You have shown those infall of material from the simulation for quadrupole plus dipole combination, for example. So you know, I had a chat with her in a couple of weeks ago, I guess, or a few weeks ago, and so what I came to realization is that, you know, because such a strong magnetic field almost invariably will lead to destruction of this circumstellar disk, and what you're seeing is the transient event. It is in the process of being destroyed. So my question is, you know, so have you actually, what are the time scales? Have you actually looked at it more carefully on a, you know, long-term evolution of that?
Not yet, because up to now we didn't have access to supercomputer. Actually, it was we were able to, or Alicia was able to calculate it only because Raul is her husband, and he gave her computation time. So that was a little bit problematic. But now Alicia has access, so she can extend the calculations.
Okay, thank you.
Okay, so we're just about rounding the hour. Is there might be time for one last quick question? Yes, Dietrich?
Presentation, as Stan already pointed out, the incidence of magnetic fields among B-type stars is 10%. And so just a dipole field is not a smoking gun, but the signature of Taos Co is that the magnetic field is very tangled. So what is the observational evidence that you have higher order structures in the magnetic field? You mentioned quadrupole, octopole, etc.
This was up to okay. A few months ago, when we analyzed the data, so look, it's only few data. So it seems that the more complicated field plays their role, but now, the phase curve shows that the dipole is the dominant one. But Alicia already started the calculation, so we finished it. Or she finished it because some her big AEB stars have complicated structure. So we just would like to see if in another star this can happen and what we may expect.
All right, so let's thank once again our speaker, Dr. Korčáková, for a really nice presentation. The presentation will be online on YouTube in probably a couple days. Thank you, Dr. Korčáková, for also overcoming the slight technical difficulties and everyone for bearing with us. But that was a very nice presentation. So we'll be having our next monthly seminar in January. It will be announced sometime soon. In the meantime, I just wanted to wish everyone a very nice holiday period. I hope you manage to get some rest, and we'll see you all in January. So thank you once again.
Merry Christmas.
Take care, everyone.
Okay, so thanks for the invitation and thanks for the possibility.
Thank you so much for saying yes.